This video for advanced biochemistry is on alkenes, initially looking at how alkenes are made, but then going on to really talk about an important reaction known as electrophilic substitution. And we will talk about three specific mechanisms in this video. So this may be a longer video than some of the others in this unit. And when it comes to making alkenes, we have expressed two ways already in which they can be made. The first one is taking an alcohol and doing a dehydration reaction. That dehydration reaction, remember, you can use concentrated sulfuric or phosphoric acid, or you can use aluminium oxide, hot aluminium oxide, to do the dehydration. The second is using elimination of haloalkanes with a base. Now remember, elimination reactions of haloalkanes requires your potassium or sodium hydroxide to be dissolved in ethanol, not in water. When it comes to reactions on alkenes, the main reaction you need to know is that alkenes do addition reactions, and the majority of these reactions are specifically known as electrophilic addition reactions. And many of them you've already covered at National 5. So the first one, if we look at the green one written in green, is hydrogenation. Now, hydrogenation means adding hydrogen, and it converts an alkene into an alkane. This is the only one you will not need to know the mechanism for, as it is done on a catalyst, so a nickel catalyst, something known as Raney nickel. The second reaction, known as a hydration reaction, shown in red, is when water is added to the double bond to generate an alcohol. This is going to be one of the more complicated mechanisms in this video, which you will need to know. Moving to the bottom right, to the one written in blue, this is our halogenation reaction. Now you're more used to seeing that with bromine, and that is your test for unsaturation. Bromine would react with an alkene and go from orange to colourless. That is because the halogen, bromine, chlorine, iodine, or fluorine, adds across the double bond. Again, this is going to be a mechanism you need to know. And the final one is one that wasn't really talked about in National 5 or higher, only in problem-solving questions, and it is known as hydrohalogenation. This is when, instead of adding hydrogen or a halogen, you're adding a molecule like hydrogen chloride, hydrogen fluoride, hydrogen bromide, hydrogen iodide, in such a way that on the double bond you add on one hydrogen atom and one halogen atom, which can lead to isomers forming. And again, that is going to be a mechanism you need to know. Now, when it comes to these electrophilic addition reactions, your halogenation, your hydrohalogenation, and your hydration reactions, you need to know something known as Markovnikov's rule. Markovnikov's rule is going to tell you where there are two possible products, which one of those products is more likely to form and which one is less likely to form. So there are two possible isomers. One of the isomers will always form in greater quantities than the other and will be known as the major product. The other one, which has a lower yield, is the minor product. And as I said, Markovnikov's rule will allow you to determine by looking at the molecule what the minor and major products will be. So Markovnikov's rule is when a hydrogen halide or water is added to an unsymmetrical alkene, the hydrogen atom becomes attached to the carbon with the most hydrogen atoms attached to it already. Now, said in words, it is very complicated. In practice, you can usually see where the hydrogen is going to go. You also need to understand what is the reasoning behind Markovnikov's rule, and it essentially is when you're following a mechanism, there will be two possible carbocation intermediates to form. The carbocation intermediate that is most stable will lead to the major product. The one that is less stable will lead to the minor product. Knowing that Markovnikov's rule is related to the stability of carbocations will be how you score marks whenever you're asked about why something is a major product or a minor product. You need to know the why, not just the definition. So here's an example of a hydration reaction on but-1-ene. Now, but-1-ene is not a symmetrical alkene. So as you can see, there are two possible products. We have got a butan-1-ol and we have got butan-2-ol as our products. Butan-1-ol at the bottom, butan-2-ol at the top. Now, in the reaction, if we look at our starting material, the carbon on the right-hand side of the double bond has two hydrogens on it. The carbon on the left-hand side only has one hydrogen atom on it. Markovnikov's rule states that when a hydrogen is being added on, it will add on to the carbon that already has the most hydrogen atoms. So it is going to add on to that carbon on the right-hand side and lead to the formation of that top product, butan-2-ol. The minor product will be the one where the hydrogen adds on to the carbon on the left side of the double bond. Now, the next part of this video is going to look at the individual mechanisms for addition reactions. The three addition reactions have their own unique mechanisms that are slightly related to one another, but are different enough that you should learn them individually. Each addition is classified as an electrophilic addition. This is because the double bond has a large electron density, making it a nucleophile. It's going to prefer bonding to positive or partially positive things, which means anything adding on to this double bond must be an electrophile that likes that electron density. The mechanisms will also help you understand Markovnikov's rule in better detail. So the first one we're going to look at is electrophilic halogenation. Now, the hardest part about electrophilic halogenation is probably the first step. Now, if we look at our bromine molecule, when it comes into contact with our double bond here has lots of electrons in it. So it is actually going to have a partial negative charge. What that does is it will push electrons away from the bromine atom that's close to it, and those electrons will move from that bromine atom closer to the bromine atom that is further away from the double bond, making that normally neutral bromine molecule polar. Once that bromine atom is polar, we get a system where the carbon-carbon double bond attacks the delta positive bromine. A lone pair of electrons in the bromine will attack the opposite carbon, and the bromine-bromine bond breaks. Those three steps all happen sort of simultaneously. So it is quite difficult to understand this one, so really focus on that. And in this process, you generate this sort of three-membered ring, carbon-carbon-bromine, with a positive charge on the bromine. It must have a positive charge because it's forming two bonds when it normally would only form one. And the other bromine ion must have a negative charge on it. The second step in this mechanism involves that bromide negative ion attacking one of the carbons in that carbon-carbon-bromine ring. So the bromine ion comes in, attacks either carbon, it does not matter in this case which one, and once that carbon is bonded to a bromine, that carbon would have 5 bonds, so it breaks the carbon-bromine bond that exists, putting the electrons from that carbon-bromine bond onto the positive bromine, turning it back to neutral. and you get your final product. So the bromide ion attacks the intermediate from the opposite side of the molecule, and because the previous bromine blocks that one side of the molecule. The bromide ion this time is a nucleophile, and you end up with a cyclic intermediate as the electrophile. The second reaction you need to know the mechanism for is hydrohalogenation, and this is a reaction where Markovnikov's rule does need to be understood. So in this reaction, what's different is that a hydrohalogen, something like HBr, HCl, is already polar. So you don't need to explain why you've got a delta positive and a delta negative side. All you need to know is that the hydrogen, because it's delta positive, will orient itself towards the carbon-carbon double bond, which has a high electron density. The carbon-carbon double bond will attack the hydrogen, and you will break the hydrogen halogen bond to create a halide ion. When you do this, there are two possible intermediates that will form, two possible carbocations. So if we look at the carbocation on the left, we've got a CH3, and an H. If we look at the carbocation on the right-hand side, we have a CH2CH3, and then we have two hydrogens. Now, in terms of stability, remember when we looked at SN1 reactions, we know that the most stable carbocations have carbons attached to the positive carbon. The more carbons attached to the positive carbon, the better. Which does mean in this case, this one here is more stable. And what has happened in this? Well, the hydrogen here has added on to the carbon that already had the most hydrogens on it. So that's what Markovnikov's rule explained. So our major intermediate leading to our major product will be our carbocation on the left-hand side. The final step of this process is relatively straightforward. We've got a bromide ion, we have got a carbocation. The negative bromine attacks the positive carbon, forming a carbon-bromine bond, and the reaction is complete. The final reaction is our hydration. The hydration reaction involves 3 steps, and so is perhaps the most complicated one. Now, what you need to remember is that the hydration reaction is acid catalyzed. So in an acid catalyzed reaction, you have hydronium ions. Now, the hydronium ions are your electrophile, and they will attack the double bond. So in this mechanism, what you show is the carbon-carbon double bond it breaks and bonds to one of the hydrogen atoms on a hydronium ion, and then that hydrogen-oxygen bond breaks to create a water molecule. Now, just like before, there are 2 possible intermediates, and we need to think about stability. So on our intermediate on the left, our carbocation has 2 carbon atoms attached to it. On our one on the right-hand side, we've only got 1 group. So our more stable one is this one on the right. And again, what has happened is that the hydrogen has added on to the carbon that already had the most hydrogens on it, following Markovnikov's rule. So we will not form that one on the right to a massive degree. It will form our minor product. Our major product will come from our carbocation that is most stabilized. Our next step will see the water molecule that we've got up here. It will attack our carbocation intermediate. So our water molecule, which has a lone pair of electrons, attacks the carbocation intermediate, and you end up with a full water molecule being added onto that carbon. And because the oxygen has 3 bonds, it is positively charged, which is not what it would like to be. So that is our second step, straightforward. You just got to remember that when the water molecule adds on, as soon as that oxygen has 3 bonds, it's got a positive charge, and we do not want that. Our final step involves removing one of the hydrogen atoms from that water molecule that has just been added onto our carbocation. How this occurs is a water molecule from the solution that the reaction is in, its lone pair of electrons will bond to the hydrogen so that the hydrogen-oxygen bond can break, getting rid of the positive charge, resulting in a hydroxyl group forming, and you've regenerated your catalyst from the start. So remember, this is your proof that the hydronium ions are the catalyst, because you needed them at the start, but you regenerate them at the end. So by regenerating the catalyst, we have done the we have completed the cycle, regenerated the catalyst, and can keep doing the process over and over again. This video has gone into quite a lot. We've looked at how alkenes are formed, either by dehydration reactions or elimination reactions. We have then looked at the 4 addition reactions. Remember, do not forget about hydrogenation, which does not require a mechanism. We have then discussed Markovnikov rule and looked at the 3 individual mechanisms for halogenation, hydrohalogenation, and for acid catalyzed hydration reactions on alkenes, which are very useful reactions to know. So that has been our completed video. Please watch this a couple of times and make sure you can do those mechanisms.